welcome to the July 2020 novice meeting of the Houston Astronomical Society. It seems like it was just yesterday when I was saying welcome to the January meeting. I think being at home during this whole thing makes the days kind of run into one another. My name is Joe Califf, and I'm the president of the Houston Astronomical Society. And along with Debbie Moran, our novice chairperson, I'd like to welcome all of our members and any of the visitors that we have visiting us tonight to this meeting. But before I hand things over to Debbie for a few announcements and to introduce our guest speaker tonight, I'd like to ask everybody, if you don't mind, to please mute your lines until the end of Tom's presentation, where, Tom, I believe you said it was okay to open it up for questions at that point, correct?
Yep.
Perfect. Additionally, there is a chat feature in the Zoom client where you can go ahead and post any questions you might have. I'll go ahead and keep track of those as we go through the presentation, and then we can ask those at the end of Tom's talk as well. For those of you who are watching through our Facebook page during the live stream, go ahead and ask your questions there in the Facebook page as well, and we'll get to those at the end of the talk additionally. So I've done all the talking I want to do, and I can't wait to hear Tom's presentation tonight. So I'll pass it over to Debbie Moran for her announcements and to let her introduce our guest speaker tonight, Mr. Tom Field. Debbie?
So hi, everybody. I'm Debbie Moran. I'm the novice chair. And we have two types of talks in this novice groups. One's really for beginners. And I just want to let everybody know, if you really need to know the basics of telescopes or sky navigation or what's up in the spring or the summer, we have a lot of recorded talks anytime you need them at our Houston Astronomical Society website. And you can find that under recorded presentations. We also do talks like tonight. Tom Field is going to talk about how to do spectroscopy through your telescope. So this may be a new pursuit even for our more experienced astronomers. And I was especially excited when he wrote to say he has this talk, because I remember when I took astronomy at the University of Texas, one of my favorite projects was making a rudimentary spectroscope with, still have a trusty diffraction grating and a yardstick, and then a scale that worked at that distance to measure the wavelengths of light from all sorts of light sources in the laboratory, and lights in the sun and on my ceiling. And it was just a wonderful experience. I also learned very much about all the information you can pull out of the spectrum, far beyond just the composition of a star. So we'll hear all about that tonight from Tom. He is a contributing editor at Sky and Telescope magazine for the past 7 years, and the author of the RSpec software. And he is based in Seattle, Washington right now. And so we're very pleased to have Tom Field. Thank you very much.
Thank you, and I appreciate, this club really has it going on. I'm a little intimidated, you know, between Joe and Deborah, there's just this real professionalism, like, go get them. Is this a Texas thing, or what's going on here?
They don't pay us either, right? So
Great. Listen, thanks everybody for coming tonight. I appreciate the introduction and the opportunity to talk. I'm going to share my screen here and then bring up another slide deck for us to take a look at. I'm actually on a different monitor than I was when I started. The other monitor I had has been having some trouble, and I thought that, geez, all I need is to screen share and have that monitor cause problems. So you all can see that prism now there, I suppose.
we can.
So I'm going to talk for 40 to 50 minutes. We've got a lot of ground to cover. I'm going to talk a little science, a little history, and then get into the meat, which is the kinds of things that we all can do with spectra. So let's get started. Let me get things just a little more set up here. I love your logo, by the way.
Oh, thank you.
So,
I can't tell you when it was designed, but yeah, it's kind of stood the test of time. Thank you.
Absolutely. So how is it we've managed to discover so much about the universe when we've barely set foot outside our own front door? You know, we can get images like this one. This is the Hubble Deep Field. And by the way, this is a piece of the sky that's the size of a tennis ball held at arm's length. It's really busy up there if you look deep enough. So we can get two-dimensional images, of course. And if we wait a little bit and are in the right place, looking in the right spot, we can see a little bit of a third dimension. We can see some depth from eclipses. And if we watch for a while, we can see a fourth dimension, time. And I think maybe you can see up there in the right-hand corner and in other places. I'm actually going back and forth between two slides. So if the period isn't exactly regular, it's not that we've made some magnificent discovery about irregular variables. These are our Lyrae stars, which are one of the standard candles. Now, if we spread the colors out, we get an as if fifth dimension. I love the colors of this. They're the real colors. They're not human-made colors. These are nature's colors. And this fifth dimension reveals the barcodes, as if, of stars. And we can use those to understand stars. Now, about 80% or so of the research that gets done astronomically uses spectra. Now, whether it's 50% or 70 or 80, doesn't matter. It's a huge number. So even if you're not an imager, it's helpful if you understand why it works and how it can be done. And so if you're an armchair astronomer and you don't go out and observe, you'll still pick up things in this talk that you enjoy. But the kinds of things that these barcodes reveal include knowing what a star's made of, what its composition is, what its radial velocity is, if it's moving towards and away from us, and also if a star is spinning. And I'll give you some examples of all these tonight. And it's, of course, its temperature and where it is in its life cycle on the HR diagram. And also distances. We can measure those, and I'll show you some distance measurements that were measurements also used by, well, a Nobel Prize winner, as we'll see. So as I've given this talk over the years, I realized that in the back of my mind, I had certain items that I wanted to cover. And I thought maybe I'd just lay them out here. So you might want to capture spectra if you remember the thrill of that first image you took of the moon. Now, if yours was like most of ours, it was blurry, it was overexposed, but it was the most beautiful image you had ever captured or seen, right? You were showing it to your spouse or your friends, your colleagues. So that same thrill is a thrill that when I got started in spectroscopy about 10 years ago, I realized I could recapture again. And it was exciting for me. That I think the brain is a novelty engine, you know, so it was very exciting. Maybe you want to do some new science with your equipment, maybe recreating some discoveries of different spectra or contribute to some professional amateur projects. You might want to capture spectra. By the way, this is more words on one screen than you'll see for the rest of the talk. This is really bad PowerPoint to do all these words, and I'm trying not to read them. So for me, somebody online in the last day I was reading, they were saying, well, I wanted to buy a telescope, but I have to get it past my credit card scrutineer. Now, I'd never heard that word scrutineer before, but again, many of us have scrutineers in our lives when we're looking to make hobby purchases. And often we're our own, and well, we should be. So what you'll see tonight is an example of the kind of thing you can do without a huge investment. The other thing I discovered is that when you actually own the data, when it's your own, you have more of an emotional relationship to it in a good way. It's a good relationship. And you tend to want to understand more about it. And things actually stick instead of going in one ear and going out the other that they do with me. Also, I don't know, maybe your dark sky sites down there are closed right now. And what you're going to see is that spectroscopy is much more immune to urban light pollution. One of the reasons is we're not really being a slave to the human eye and the aesthetics. With science, looking at spectra and peaks and dips, we want the data pretty much the way it hit our telescope. So there's not a lot of fine tuning. For me, I had done some imaging, like many of you have, I suppose. And I had one of these books, maybe you're familiar with it. It's a large format book, 8.5 by 11. Let's see if I've got it over here. I don't seem to have it, but, it had these examples, right page, left page, before processing some great convolution process and after. And I'd look at those and I go, I guess I see a difference, but it wasn't something that excited me. On the other hand, I'm the beneficiary of those features when I see those beautiful images that some other people capture. And you might want to do spectroscopy if you want to do a little science with your telescope, but you don't have a PhD. I'm a knuckle dragging programmer. And the nice thing is you don't need to know a lot of science, and there's lots of ways to learn what you need to know. And for me, I don't have the patience, skill, equipment, dark sky sight, any of that stuff that I would need to do hours of integration time. And I'm going to show you some images tonight made real time with video. And I think you'll see it's remarkable what can be done. And I also break just about everything that I touch in hardware. For me, my favorite keys on my computer are edit, undo, or Control Z. Wouldn't it be nice if we had an edit undo in life sometimes? Just saying. But what I'm going to show you tonight also, although there's plenty of do-it-yourself projects, you're going to see things that are easy to set up. And if you like doing outreach, you like mentoring, this is a great topic. So keep all these in mind. And the number one reason, number one only because it's the last of them, you want to hang out with a cool crowd. Now, I'm not one of them, but there's a huge community of people doing this, a lot of online communities. And if it's been some time since you learned something new, I can see some of you here I can see have been around in astronomy for a while, right? So when you last learned something new, it might have been decades ago. And that, even with a good club like the Houston Club, I know flattery won't get me anywhere with this group, you're tough. But even with a club, it can be hard to learn all the things you need to know. Of course, these days with the web, it's all easy. Okay, so I'm going to do a little bit of history here. I'm going to jump around in time a little bit, and then a little bit of the science. Most of us know that Sir Isaac Newton split light using a prism and discovered that it was made up of all the colors. And you can also split light by bouncing it off of a finely lined surface, like a DVD, or even passing it through a finely lined semi-transparent surface, piece of glass that's got etched lines on it. So back in 1814, this crew here, including Fraunhofer, here they're looking through a spectroscope at the spectrum of the sun. Fraunhofer discovered the spectra of the sun and that star spectra differed from one another. They didn't know what they were looking at, but it was something of interest and led to the discoveries we're about to discuss. But before we look at those discoveries, I want to rewind about 500 million years ago. Now, some of you are going, wait a second, I didn't sign up for whatever this is, paleontology? So, but look at that surface of that fossil. You see all those striations? Well, this guy, Professor Parker, saw that and he said, you know, that sort of looks like the finely lined surface that would produce multiple colors like a reflecting DVD. And so he said, what would an animal look like and why would have that occurred in the history of evolution? So he said, that's sort of what maybe it could have looked like. And in this era, 500 million years ago, there was a huge explosion in diversity. And so he said, you know, it doesn't make any sense to have all these diverse colors unless they're eyes. So maybe the two co-evolve together. Okay, let's get back onto the science, our science track. Talk just real briefly about things many of you are familiar with and can probably explain equally or better. Bunsen, of course, invented the Bunsen burner. Now, the Bunsen burner, which we have here, he invented to burn samples here, go through a spectrum with the light and look at the result. And he was a pyromaniac. He burned everything he could find, almost literally. And he was noticing, and the reason he did this is because he saw different patterns of light. And we're going to look at those patterns tonight and what they can reveal about a star. Now, Kirchhoff over here was a contemporary. They knew one another, and Kirchhoff formulated some rules to help us understand what we were seeing. We're not going to get into a lot of the science tonight, but the one thing I wanted to point out is if you look at this spectrum, notice it has a rainbow with some dark lines. Those are called absorption lines. But if you look at this spectrum down here, oh, what happened to my box? Then you have a dark area and some emission lines. The interesting thing about these is the lines are in the same position for a given star or material. What differs, and the reason we get lines like this, is because of reasons we're not going to discuss, but the temperature of the gases, the air is, the light is going through. I don't know if you just heard that, some reminder. Oh, it says I have a talk to be giving that I'm now 15 minutes late at. Okay, let's move on. So these are chemical fingerprints, and you can see that each type of element has its own line. So this line exists in hydrogen, but it doesn't exist in helium. Bear with me, this is a review for many of you, but we'll move on past this in just a moment. Now the hydrogen lines are so common and so important to us that we've actually given them names. Hydrogen bomber lines, and there are the names of them, just our standard Greek names. We'll be seeing those because they're like a lighthouse. They really help us navigate. You're going to get tired of hearing those hydrogen bomber lines in the next few slides. So I wanted to show you this. This is a periodic table. This is the last chemistry diagram we'll look at like this. This is actually a poster that we created here in Cell. You can see there hydrogen, there's those bomber lines, hydrogen alpha, hydrogen gamma, hydrogen beta, vice versa. But look over here, the helium lines are very different, right? And if you look over here, for example, the lithium in your cell phone battery, it's got very different lines. So all the elements have different numbers and brightnesses of lines. And we can observe them without burning them in a Bunsen burner. But before I show you this slide, in fact, let's go back so you're not reading all the fine print. I wanted to tell a quick story about Bunsen. And that is, when he invented the Bunsen burner, he proclaimed, that's quite a word for a scientist to use, that he was not going to patent it. He said, I'm going to release this for anybody to use with no patents, no intellectual property. And he did that for the good of humanity. Now, today it would have had 10 patents on it, right? And we would have been paying for every one we fired up. So it's an interesting attitude that they had not that many years ago. Okay, so instead of burning gas like Bunsen did, we actually have gas tubes that we can burn gas in. And I've got one over here that I'll show you a little later. There it is over there. It's a gas tube. You can see, I don't know if you can see that light. Yeah, I guess you can. I haven't shown the gas tube in a talk before, but I thought it might be fun just to show it in passing as we move through. Down here, you can see the hydrogen bomber lines. There's the hydrogen alpha, beta, gamma. Getting the idea about those bomber lines, I hope. So now, we actually sell a little tripod-mounted spectrometer for educators to use in the classroom on gas tubes. And we did a fun project, by the way, at your state with the University of North Texas. They run 2,000 liberal arts students a year through a lab doing spectroscopy with that device, as well as with the other things I'm going to show you. It's an unbelievable number. So a little bit before Bunsen's time, this French philosopher said, we're never going to be able to study the stars, they're too far away. It seemed very reasonable at the time, but several decades later, all sorts of people were capturing spectra of stars, and we were beginning to understand the stars. So again, we have somebody from Italy here, we have UK here, the French have always done a lot of spectroscopy. So Comte was wrong, but of course paradigm shift and people learn new techniques and new science. It's interesting to think 100 years from now what the science will be and how they might look back on us and go, they didn't know this. Can you imagine how primitive, not primitive necessarily, but how starved they were for knowledge, and maybe things that they're doing 100 years from now, we would have wanted to be doing now if we only had that knowledge. So, so far, every astronomer I've mentioned has been a white male. I'm going to show some of the women who have contributed to this field. Annie jumped cannon, like her group of computers, were women who were prohibited from getting access to telescopes. And so, to our great fortune, and maybe theirs, instead of late nights in front of a telescope, they got to work during the day examining glass plates of spectra. And through their diligence and exactitude and creativity, they came up with the star classification system that really helped us understand the evolution of stars. Nancy Grace Roman was a woman. She was the first astronomer for NASA. She got her PhD in the late 40s, and the Hubble Space Telescope was her vision, her dream. She made it happen. Really remarkable. And Elisa here is a modern day current astronomer. And because I don't speak Spanish, I'm not going to try and pronounce her last name, which is unfair of me. This is only the second time I've done this slide in the talk. I'm going to learn that name before I give my second talk tonight. But she is an exoplanet discoverer. She discovered an exoplanet around a late stage or a cool star, and the planet's at just the right distance that it could have liquid water. And so, you know, there could be life there for all we know. So how do we get, and again, bear with me, we're almost done with the science. How do we get absorption lines? Well, the Bohr model has electrons circling in shells around the nucleus of the atom. And when they jump between levels, they give off energy, right? Just like when you drop a ball on the Earth, once it's reached the Earth, it's less energetic. It doesn't have that potential energy in it. And some of that energy we can see as spectra. Different jumps produce different colors. Look, there we got our hydrogen alpha, beta, and gamma again. So that's the spectral lines for hydrogen. This is a picture of Einstein that I love only because, and he's with Bohr. Look at his posture there. I mean, is he kicked back or not? Okay, here's some examples of some professional spectrographs. The one on the right in France discovered the first exoplanet, and we'll look at an example that shows how that's done later. Here's a spectrograph down in Chile. It looks like just a lot of equipment until you look at how small the people are in that view. And this is the Hubble spectrograph getting serviced by the space shuttle. Now, My son says that's not a spectrograph. He says that's a refrigerator. It's filled with beer. And at night, which happens fairly frequently on the space shuttle, or did, they are party animals and they're drinking beer. Now, I can't prove him wrong, but I think he probably is. So here's an amateur device. Dale, I think, regrets having ever shared this and given me permission to use it. It's far more complicated than any of us typically need. What I like about this device is down here is a gas tube that he's shoved into the telescope. And in particular, what I like about it is these pins that are right there. You think about a neon type tube, it's got two little pins on the end. And I picture Dale with like two high voltage alligator clips, clipping them on those pins. And the problem is, if he draws a spark, he ruins his night vision, right? So what I want to talk about tonight, now that we're through most of that technical stuff, is I want to talk about this grating here, which is a diffraction grating. It has 100 lines per millimeter, and you can see it there. And now I am going to try, I tried it earlier and it seemed to work. I'm going to turn on our gas tube, and I'm going to hold this up, and you're going to see, oh, there it is, in the upper, there it is, diagonally. You can see a spectrum. There's actually multiple spectrums end to end there. You see some red and some green. So this is splitting light. It's an 1.25 inch grating, and so it will thread on to most any camera that you've got. And we're going to talk about how you can use that to do some of the things we're going to look at tonight. It costs $200. So here's the first example I wanted to show you. It's got the star analyzer on a DSLR. Notice there's no tracking. Even though there's no tracking, down here we got a spectrum. And what do we get? Hydrogen alpha. Yeah, you're getting the hang of it, I think. Hydrogen alpha, beta, and gamma. So this is a little hard to do because it's a drift image, so you got to get things aligned in a small aperture. So I show that as an example as to how simple things can be done. But it's not the preferred manner at all. There's lots of other ways to mount a grating on a telescope or a camera. This is the one I just showed you more or less. And we actually have a little adapter. That's a terrible arrow, that screws into the lens cap threads of a Canon camera so that you can mount it that way. It's called an objective prism in that configuration. You can also use a standard fits camera. The camera can be color, can be mono, can be a video camera like this here. This is a ZWO camera. Not that you need to see one since you're probably familiar with these kinds of enclosures, but it just, as you can see, in this case, it just threaded right onto the nose piece. And you can also put it in a filter wheel. So there's lots of ways to mount these things. There are higher resolution devices. You can see they're also higher priced. These devices have a slit. A slit is a great thing. It creates higher resolution spectra, but it also means you have to acquire a target and guide on typically a 20 micron slit. It's harder to do, they're harder to use. 1 in 1,000 people seem to start with one of these. Most people start with a star analyzer and learn the ropes that way. Some people do both. You can see a star analyzer piggybacked on the telescope, and down on the bottom here, you can see a higher resolution device. That's like a $3,200 device. Okay, whew, now we're done that sprint. So we've seen the history, theory, equipment. What can we actually do? That's why you're here tonight. But now we've got everybody to the same level, so I appreciate your suffering through that. So we put starlight through a grating, we get a spectrum. And we can capture that spectrum on our camera. Here's our first example. This is a series of different spectra. These were captured by Torsten Hansen down here with an 8-inch telescope and one of those imaging source video cameras. So we're not talking long exposures here. So these are in temperature order. So these are an OB of fine G, kiss me order, right? So there's type B, type A stars. So for those of you who aren't familiar with this, the stars were classified originally by the women that I showed you in that earlier slide by temperature order. And there's a reason the letters are this way, but it's a historical reason. We need not get into it. The stars at the top are the hottest stars, and the stars at the bottom are the coolest stars. Take a look at that. Now, you see those differences? So different stars have different spectra. So we're already able to do a little science and tell something about the temperature of stars, right? So down here, these stars, these cool type M stars, have these wide bands, right? But these stars up here, they don't have bands, but they have this, which is hydrogen beta at about 4,000 angstroms. But notice this hydrogen beta is darker and wider on this type A star. So A stars seem to be just the right temperature to get the most number of electrons jumping between shells, creating that absorption line. These hot stars at the top, they are a little too hot, and the electrons, a lot of them just bounce right out of the star as if. And these hot stars, yeah, that's right. And these stars down here don't pump up enough energy to get those electrons to jump between the shells that cause that line. So this is, again, now we're looking at star temperature as well as composition, right? If we're seeing hydrogen lines on a star, the star has hydrogen somehow. So now if I was to show you this and look at that spectrum on the sensor there and see that crosshairs down there, if I was to show you that, I don't know how many of you can see that it's a little bit dimmer between those crosshairs where they cross. Can you see that, people with video? Yeah, Joe's nodding his head, thank you. So to do science, I can't write a paper that says, yes, we used the Hubble Space telescope, and we saw a little dimming in the robin egg blue. That's not science. What science is actually quantifying that data and representing it. This is an intensity graph. We'll spend just a moment looking at it because this is the way we look at spectra. So this star is really bright, so we have a really bright peak of data here. And this thing goes from dim, bright, 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 dim, right? It's much brighter here in this green area. So this goes from dim, bright, bright, bright down to dim. So the cool thing is that dip in the red curve is quantitative. Now we can study its width, full width, half maximum, its position, what color it is, how it compares in size and depth to other stars, to other elements. Now we're doing science. So how do we create those spectra? So this is a software that I wrote. Again, let's come back here so you're not reading screens while I'm talking. So, so that night I went out here 3 miles from downtown Seattle near Seward Park, Sheena. That's rather awkward. It's like an old Firesign Theater album. Hello, Clam, if you're familiar with that. But let's move on to something that actually interests people. And that is, I went out at, 10 at night, late at night here in Seattle because the sun sets so late. In my backyard, I came in at midnight. I'd been looking at Vegas, so my blue jeans had grass stains on the knees. Next morning, I was all excited to look at my spectra. I looked at some of the freeware that was out there, and literally 2 hours later, I gave up, literally here, threw the star analyzer in a drawer and said, I don't want to do this. I'm not having fun. The software is hard to use. It crashes. It's in French. There's no manuals. And I gave up. But I really wanted to do spectra. So over the next week, I kept thinking about it, and I decided, okay, this weekend, I'm going to write a program to convert the colorful rainbow spectrum into a graph. And now, what, 5,000 to 10,000 hours later, the software is almost done, almost. So I want to show you really briefly the software running. This is not a software demo. We're going to get back to real stuff in a moment. This is real in some ways, but here's the software. And I hope you can see that screen. I hope, Joe, you can see the software screen. Great, thanks. So this is the image. It's in color, but it need not be. Color makes it easier to understand what we're seeing at first. Color cameras aren't as sensitive as you know. It could be a video. It could be a FITS image that our software will automatically load whenever it hits your hard disk or solid state drive. There's a star, there's a spectrum, there's some gaps, there's a big gap there. So now if I drag these sampling lines around that spectrum, we get the graph I was showing you earlier. This peak is the star, and this broad thing is that, and that broad dip there is that. So now we're doing science. So, and this is in some steps I won't show you during my main talk. This axis is calibrated in angstroms. It's about a 20-second couple of clicks to do. And now we see those dips. Now the real issue comes up, and I think this is a disincentive for all of us, including myself, when we get started. It's like, well, how do I know what those are? Well, one thing you can do is build into the software is a library of measurements like Bunsen made. So we can say, show me on the graph in an overlay where the hydrogen bomber features are. And look at that. We've got a line going through our dip there. We've got one going through there. That's our hydrogen beta, hydrogen gamma, hydrogen delta. we've pretty well established that this star has a lot of very visible hydrogen absorption lines. That's the science that's fun to do. Now, the other thing that we can do here is we can add some eye candy. And this is actually a frame from a video. This is the last thing I'm going to show you in the software. Let's play that video. You can see the image here, the graph is jumping up and down because our data is jumping up and down from our scene. The video is playing at 2 frames a second. This is like light to moths when you're doing a star party or some sort of public outreach. So when we get back to that, this is the kind of thing that people really want to know what they're seeing. It's a very interesting screen to show them. Okay, let me pause that and come back to the show, and we'll dive into some examples. So this is a wide field example with a DSLR. I wanted to show you this first because it's beautiful. Secondly, to show you there's some emission lines, right? Some bright lines. And there's some absorption lines. And of course, the parent stars are over here to the side, to the left. So when Janet Simpson sent me this spectrum, she was in the UK, and you can see down there, she did this with a Canon and just 30 seconds with a mechanical tracker. I have a confession to make to the group here. I couldn't remember what a Wolf-Rayet star was. Now, I'd read about it countless, maybe 5 times in 20 years, but like I said earlier, things go in one ear and out the other. Well, Wikipedia is your friend. Wolf-Rayet stars are late-stage stars. A lot of the outer shell of gas is gone. So we're able to see beyond that outer shell where we'd see a lot of hydrogen, down into the core, and we see a spectrum like this. And this spectrum is showing us a fair amount of carbon, right? There's carbon there, ionized carbon there, there's some helium, there's some more carbon. We are looking down towards the core of the star. This carbon is the byproduct of that star's life cycle. And we're seeing it with an amateur telescope, with an amateur DSLR, 3 inches of aperture and 30 seconds of exposure time, tracked. Pretty amazing. So if we were to use a star analyzer in our beloved M57, for those of you who aren't familiar with this, now I got to get it right, it's a shell around a late stage star also. And that's what the spectrum would look like. Because there are only 2 things glowing on this star, there's really only 2 objects on the spectrum. But if this was a broad, much bigger object like a planet or a galaxy, there'd be lots of colors. And because it was extended, they'd be all smeared all over each other there on the right. So one of the drawbacks of an inexpensive device like this is it doesn't have a slit. So you have to image objects that are like, what am I trying to say here? They look like they would appear in a slit, meaning very small. Let's look at an object like that, M42. Again, they're all beloved to us, right? These are our showpieces. And here we can see same kinds of emission lines. They're very narrow here, even though it's a really broad object, right? So what I want to do here for a moment is turn off my screen share. Meeting controls are here. And now I want to have just a real brief discussion with you all. First of all, for those of you, and you probably all know this, but in case certain groups don't, if you're only seeing 5 or 6 named or video displays across the top of your screen, then go up to the upper right-hand corner and click on that button labeled Gallery View, and you'll see 25 videos all simultaneously. So I wanted to ask a couple of you, hopefully with video or not, to unmute your mic and just tell us when you first saw M42 and what it looked like. It's sort of fun to hear. Any takers? Don't be shy. Bueller, anyone?
I'll go first.
1975 in a 6-inch telescope. It was a gray cloud.
Yeah, it was. Anybody else?
I was going to say a 2.5-inch telescope, probably in the mid 80s, and looked like a smudge.
Yeah, it looked like a smudge. Thanks for those answers. Bill, was that your telescope you were looking through or somebody else's?
Oh my, I didn't have one yet. My brother's telescope, yeah.
I hear
6-inch reflector.
Good. And these guys aren't shills for me, but my story's the same. And the reason I wanted to bring this up is because I was at a star party in Denver. It was just before Shoemaker Levy 9. That's how I got into all this. And they had these things out there on the observing field that looked like the cannons in the circus that they shoot people out of. You know, they were daubs. But what did I know? I didn't know what I was looking at, right? So, and the reason I like this live video, and not to make anybody self-conscious, is I got a laugh there from the Goldberg. So I think I'm on track then. So when I got up to the telescope, there were people like all of us showing different objects, and everybody, all the narrators were excited. And I got up and I looked through, and I would use that word myself. It was a smudge. I was really disappointed. And I dare say that most of you have a similar experience. But here's the deal. I bet Bill and Joe and most of you still go back and look at M42, right? And one of the reasons you do that is because you're much better at averted vision. And I had a visual aid here, which seems to have disappeared. So it's a stupid one anyway, so we'll skip it for now. But you also go back because you know what you're looking at now. And when we bring that understanding that we've gained over the years to the eyepiece, our experience, as you all know, gets that much richer. So it's right now we know M42, for those of you who aren't familiar with it, it's a stellar nursery. There's gases, clouds, and they're glowing, and stars are being born. And it really captures the imagination for us nerds. So the reason I bring that up is because spectroscopy has done the same thing for me. Is as I've read about the different objects I've captured spectra of, I've learned more, and that learning has deepened my visual experience as well as my imaging experience. So let me go back to the little show here. Give me a second. Great. Okay, so let's move on, look at some other examples. This was also done by that guy with the imaging source camera. It's Uranus and Neptune. Notice the bands there, and notice the deep dips here and the bands visually. This is the methane gas on these planets. This is remarkable on a backyard video camera telescope. So think of astronomers 30 or 40 years ago. If you told them with an 8-inch telescope you could get this kind of spectra, they would have given their left leg, right, to be able to do this thing. So another example of the kind of thing you can do. So here again, our beloved showpiece Berio, we're getting back to the space shuttle there, or Berio. All I want to show on this slide is that you can see that the hotter star has more energy over in the blue end of the spectrum. So this is that intensity plot that we looked at my software creating. And in the late 1800s, Henry Draper captured the spectrum of a comet. Well, if Hank can do it, so can we. So here's a really nice string of jeweled colors on this comet. Now, the comet is an extended object, so by all rights, I've already said you can't look at extended objects with a slitless grating, but this is a compact enough object that you can. So some comets you can, some you can't. Over here, we can see the carbon swan bands. This was captured by a guy, Vikrant Agnihotri. He's a nuclear power plant engineer in Rajasthan in the northeast part of India. He's a great imager today. So now anybody who uses a C-clamp as part of their setup is my kind of do-it-yourselfer. Of course, I would tighten mine too hard and the enclosure would pop open probably. And you can see the star analyzer on this video camera. And down here, we have our spectrum. It's one frame from a video. The meteor was traveling that far in one frame. And at this moment, there was a bolide. It got bright, and he captured this spectrum and identified some of the minerals in that spectrum. Pretty cool. This is a subset. This is even more challenging than some of the other hard things people do. But for some people, it floats their boat. So it's fun to see. So I'm not going to spend a lot of time on the flash spectrum now that we've had a total eclipse in this country. But again, when the sun is just about totally eclipsed down there in the lower left-hand corner, it's no longer an extended object. It's now narrow. And now we can capture the spectrum. And here is where we can discover helium. And if you don't know that story, it's a great one, and one of your friends can tell it to you. I'd love to tell it, but we've got a lot to cover. There's the helium we discovered. So you can capture the spectra of novae, and notice this nova has some iron in it, and this one doesn't. So there's science going on there. So Doppler shift. You know, I'm really sort of bummed out by that missing prop. So during the Q&A, I'll get up and find it. But just to review for those of you who aren't familiar with Doppler shift, which is similar, or is a name for the change in pitch that a car horn or a train horn coming towards you goes through as it goes past you. So it's high pitch as it's coming towards you, and as it's low pitch as it's going away. It actually changes in pitch by that movement. And so whether it's sound or light, we get the same thing. So if something is moving away from us, we'd expect the spectra to be here, but it's shifted over to the right. We have redshift in the spectra. And that's how the first exoplanet was discovered in France. They looked at the spectra over time of a particular star, and they saw the spectrum going back and forth over a period of time. And how does that happen? The way that happens, and I could use a good prop here too. If this is a star and this is the planet, the exoplanet, and the exoplanet is going around like this, the exoplanet, even though it's tiny, is dragging the star towards you, away from you, towards you, away from you. And guess what? That gives you Doppler shift. Red shift, blue shift. So these days, amateurs can detect planets using photometric measurements. The amount of shift that occurs is very small on objects in our solar system or even in our galaxy. However, there are some objects that's not the case for, that are moving fast enough. We haven't had any supernovae here that are catching our imagination, we were hoping. So supernova, just very briefly, and again, I apologize to those of you who know far more about this and could explain it better, or know far more and don't want to hear yet another explanation. Two stars orbiting each other. We won't get into the details, except one of the stars becomes a giant and has a lot of spare gas as if, and some of its gas spills or is gravitationally attracted to the small star. And when you throw gas on something hot, it explodes and you get a supernova. Supernova are enormously bright. There's one in M101. And there's what a supernova of this type looks like. It's not this supernova. And that's the expanding cloud. I love that image because we recognize that as likely to be a sphere that's spherical, as most spheres are. So there's the spectrum, and there's David Strange's equipment, which I want to point out. 9-inch Celestron telescope, star analyzer grading, and less than 15 minutes of integration time. When he looks at this spectrum, he found a little absorption feature right there. And when you look at it in the software, it's there. Now, the shoulders upon which we're standing and the heads that are on those shoulders have figured out that type 1a supernovae, where you have these two stars, one dumping gas onto the other, occur. You get a very deep dip from silicon. And that dip David measured on the x-axis at 6150. Now bear with me, 4 lines of math, nothing fancy. There's the number that David Strange measured down in the x-axis, right? 6150. So there's where the dip would be if Bunsen burnt silicon, like beach sand. Those numbers are different. So we have some Doppler shift. When David sent me this spectrum, I went to Wikipedia because I didn't know the Doppler shift formula by heart. Maybe I did 40 years ago. I doubt it. And there are the numbers plugged in, and there's the result. That's blue shift from the shell coming towards us at 22 million miles per hour, measured on a 9-inch telescope in the backyard in less than 15 minutes. There should be 2 wows here. One is, wow, that's fast. The second is, wow, I can't believe I measured a spectrum with such simple equipment. Now, some of you are familiar with Adam Rees, who won the Nobel Prize in 2011 for work he and his team did just before the turn of the century. I wonder whether this feels like you're drinking from a fire hose here, and whether that's good or bad. This is being recorded, and you can go back to it. And I'm going to also give my email address at the end. So I love the topic, as you can tell. So don't worry if you're missing things. We can have a chat about it afterwards or at some other time. So he won the Nobel Prize, as many of you know, for measuring cosmological expansion, speeding up. And he used these type 1a supernovae as his standard candles. And we've just measured a supernova and its radial velocity of its shell, anyway, on backyard equipment. So here's another quick example. These are plots day by day of a supernova. There's the same dip we were looking at of ionized silicon. You can see as the days go by, it shifts back to its resting wavelength, and it gets more flat because the shell is thinning out. And so we are able to see through it to the star itself. Okay, So this is a black hole. We're not going to get into a lot of theoretical discussion about black holes, except they can be enormously bright. An example of that is black hole 3C273. These were named as quasars in their original naming because they were quasi-stellar objects. We didn't know exactly what they were. David Hayworth captured this image with a similar exposure time, about 15 minutes integration. There it is. I've never seen 3C273 myself, or its spectrum. You can see the two dots where those arrows are pointing, and there they are blown up. When we plot it, we get that plot. And this guy, who was 25 years old, or in his mid-20s, in the mid-60s, he stared at this, and there's a fantastically interesting transcript of an interview of his, the link to which is on our site, but I can also send you. I think you'd enjoy reading it. I don't know any easier way to deliver it to you. I guess I could have a tiny URL here with it on it. But he describes staring at this and the science and how science works. First of all, lots of frustration, can't figure out what it is, decides after pulling his hair out that, well, at least, let's just eliminate it being hydrogen lines. So he pulls up a spectrum much like the one I just showed you. In fact, this is the one I just showed you in my software. I forgot I want you to look at it and remember it. And he went, well, no, those don't match, except they do match, but they're shifted way to the right. There's a lot of Doppler shift going on here. And this shift is from cosmological expansion. In fact, when I wrote my first article for Sky and Telescope in 2011, I called this redshift. And the editor-in-chief of Sky and Telescope, Bob Noyer, sent an email to Rees, the Nobel Prize winner I mentioned in the previous set. He hadn't won his Nobel Prize yet. And I asked him, he said, now Tom wants to call this redshift or Doppler shift. Is this Doppler shift from speed, from velocity? He said, no, there's nothing moving here. There's cosmological expansion going on. It's an interesting distinction, a subtle distinction, the way words work and the way scientists use words to be clear about what they're talking about. So we can measure the cosmological shift of this quasar with a backyard telescope. The amazing thing to me is, and what this discovery was, by the way, was that this object was so far away, 2 billion light years away, but still bright enough that we could see it, which meant it was enormously bright. That was the discovery. But he was so scared because it seemed so obvious from this, and he was scared just like many of us, most of us are, when we go out on a limb with something that's new and novel. He was scared, and he talks about in this interview, he was worried he was going to be laughed out of the academy because he made a stupid mistake and there was an easier way to explain this. But he published it anyway, after conferring with some colleagues who agreed with him that this was the right interpretation. 2 billion-year-old light that still has enough information in it that you can understand something about the original object and how it got here. That's amazing to me. There are other things in the universe that do not age as well. Here's Martin Schmidt a few years ago. Now, I live in a glass house, so I shouldn't be throwing stones, I know. But it is remarkable what can be discovered with such ancient light. Now, so far, we're just about to wrap up here, my presentation. So far, we've been looking at features like these, the hydrogen bomber lines. How wide are those lines? Let's just take a look here. Let me bring up my pointer here. So if we drag down to there and to there, what's the width of that? It's about 50 angstroms. But if we want to drill down into the details of one of these, zoom in, we need a lot higher resolution. And that's where you end up using a slit spectrometer. And here we have two spectra, one of Vega and the moon. And you can see this major dip, this hydrogen alpha dip, is in different positions because Vega is moving towards us, blue shift, and the moon really isn't. So we compare a known stationary object to an unknown moving object, and now we can measure, again, the radial velocity. And that's another way that we can, well, as I mentioned earlier, we can detect an exoplanet. So last example, I've actually got a visual aid here. Oh, and while we're talking about it, I've got two visual aids. This one I should have put on earlier. It is a spectroscopy talk. They tell you to dress for success. And that's their hydrogen beta line right there, I think. And then the gamma So anyway, now I have a little problem here. I know it's here somewhere. I had like, you know, I haven't been able to get to my stylus in like months. You know, they're not, none of them are answering their phones. I don't understand. So forgive me for the look. So over here, I have a star, and that star is rotating. So the light coming off the star here is coming towards you as it comes off the star a little faster, a little sped up as if. And the light over here as the star rotates is a little slowed down, right? Because the star is rotating away from you. So you have a smearing. What would normally be a very deep dip here is spread out and smeared on, let's see, which is that, Altair. So now we're measuring the rotational speed of a star. This also requires a slit to get that kind of resolution, but it's pretty cool that you can do it. Okay, so how do you get started? Very simple. I've talked about the star analyzer grading here. You need almost any camera. It's not as important as focus, but this distance from the grating to the sensor in the enclosure of your camera needs to be in a certain range. And so you may need a spacer, number 3 there. And there's a calculator on our site. It's a little bit of a speed bump to get over as you get started. And so I'm always here to help people figure out what would work with their equipment. You know, in the UK, somebody was recently telling me they don't call them speed bumps, they call them sleeping policemen. So it's funny how different cultures have different expressions like that. And finally, you need software. My software, which I showed you, RSpec, stands for real-time spectroscopy, because you can do real-time video. You can also have, as I mentioned, FITS images or raw DSLR images automatically loaded into the software as they hit your hard disk. So there's lots of resources. The one I just wanted to flash in front of you, and they're all listed on the site, is this. And the cool thing about this is, because I mean it, as I said earlier, I was worried, will I understand what I'm looking at? How do I interpret it? So this book is great because it's got, let's find a great example of it. Let's find one here. It's got sample spectra with various things called out in them, and which are worthless to most of us, including me, because I don't know what I'm looking at. It's got the pros to explain what we're looking at. And so even for an armchair philosopher, yes, but like that Frenchman who was wrong, even for an armchair astronomer, this is an incredibly valuable book. There are video tutorials for my software on the site. In fact, the software is free for 30 days on the same link. It's this one here. On this download link, you can download the software, as well as a link to a 1-hour YouTube video of me giving a workshop in person to the AVSO a few years ago at the SAS in California. Sample data is there. You can go through all that on your own for fun. And there's, as you can see at the bottom there, the AVSO has jumped with both feet into spectroscopy. They have their own database for it now too. There are opportunities to do pro-am collaboration. Not as many as all of us would like, but there's more and more, and the AVSO is going to help us get there. So we've come a long way in the last 45 minutes, as well as in the last 3 centuries. Fraunhofer, you may recall from an earlier slide, discovered spectra of stars, invented the spectrograph. Kirchhoff to the right was a contemporary of Bunsen's and helped us understand what we were seeing. We do stand on the shoulders of giants, and it's amazing the discoveries. I think I might have used that word amazing too many times tonight. The other thing I wanted to mention was I wanted to thank the club because looking at your site and talking to people about it beforehand over the last several weeks, I know the club and a lot of you do outreach and educational work. And in my mind, that's one of the most important things we can do, especially because we have the science and we've all had the opportunity in our lives and the privilege to be able to learn what we've learned. It's nice to give back. It feels great, as you all know. So I'm mostly singing to the choir, but I wanted to thank you for all that. Thanks for your attention tonight. Thanks for smiling at my jokes. I'm here, and I'm happy to answer any questions, Joe, that they chatted or that they may have that they want to say out loud. There's my contact information also. Thank you again.
Wonderful, Tom. Thank you so much for that presentation. That's you said you can't use the word amazing enough. I think that was an amazing presentation. I'm ready to go out and start doing this myself. So if you want, folks, go ahead and unmute yourself so we can ask some questions. But we did get some through the chat room that we have. Bill asked first, how can we get some, quote, inexpensive gas tube type of targets?
Yeah, good question. Well, this this here is, there. This is, oh, my camera's on a different monitor. No wonder. This is a gas tube that costs about $30. The power supply costs a couple hundred. I can give you the names of some suppliers if that's something you want to do. It's not real exciting as an amateur to do a lot of that. After a while, they're always the same when you pull them out. But they're not really necessary for us because we don't need them to help us calibrate our spectra, a topic we didn't get much into. I wonder if that answers your question or whether there was more to it.
Well, what kind of place would I get gas tubes like that?
Oh, okay. So the place I recommend is called Arbor Scientific. They're out of Michigan, and they're very responsible, good people. I've worked their booth at a variety of educational shows. And I can send you a link if you want to send me an email. I can send you a link to the actual products. If you're going to do that, just a brief advertisement for this thing that I showed. This allows you to capture spectra on a lab bench. You may want to just do it with a telescope or DSLR, but this just plugs in and has a video camera in it. Same software as the astronomers use. Anyway,
Todd, are you sharing a screen right now? People are saying they just see
no. A good question. All I'm sharing is the little stamp.
Okay.
That,
I think
that they can see. I think
we're just seeing
all
the
I
blue
can
screen.
see now is a blue screen.
Oh, my apologies. Let me stop sharing my screen. I really appreciate your pointing that out. If I can
no problem.
If I can find, Zoom is so easy. Meeting controls.
Yeah, Zoom is easy.
There we go.
So Justin McCollum asked, is that large red curve correlated to the source's black body radiation curve? And I think that was when we were watching the where you showed the first slide of a spectra.
Yeah, a great question. And for that, I'm going to share my screen again. Sorry.
Sure.
I'm not
Just in time, right?
Yeah, this happens. So here's what the question is. The question is, stars have a particular shape of their curve depending on their temperature. Not only the dips, but their shape. And that shape is often called a Planck curve, even though in truth, stars are not black body radiators. And this curve doesn't look like a star's Planck curve would look like. And let's see why it doesn't. Let's see why. So the software has built into it a reference library of all the different stars, O, B, affine G, K, M. There they all are. So let's bring up a type A05 star, because this is Vega. So now in blue, there's what the star should look like curve-wise. And in red, or green now, that's what it looks like. So the question is, the questioner is saying, first of all, does the red curve reflect the blue? And my answer is no, it doesn't. And the reason it doesn't is an interesting one. And that's because our cameras are more sensitive in the green and lose sensitivity as we move into the blue, as well as red. So that's why this curve drops down. But the good news is we can correct this curve. This is a curve from a professional who's already corrected it. This is the Planckish curve. By the way, the reason this isn't a Planck curve is because there's all this energy over here you have to accommodate. You have to account for if you're going to use Wien's law, for those of you who are familiar with that. So the other reason it's not a Planck curve is because the starlight could be coming through some reddening dust on its travel coming towards us. All those are fixable, but so there is a way to correct our curve so that this curve looks like type A star. And I have, just for a second, let me see if I can find it. ALBERIO. Let me try one more time. ANP something. Here we go. So I'm going to show you a video of Alberio A and B that demonstrates that, and I'll narrate it as we go. It's pretty cool. So if I can get it onto the screen. So here is the corrected spectrum of Alberio, the dimmer of the two, which would be B. And notice it's got more energy because it's been corrected over here in the blue. But if we run the video a little longer, I'll move the sampling lines to the other of the two Alberio stars, and it's got all of its energy over here, or not all of it, but more of its energy over here in the red instead of the blue. So now again, it's a secondary way of detecting star temperature. I hope that answers your question. If it doesn't, I'm happy to get into more detail.
Absolutely. I think Justin had asked that question. There was another question from Jeff Kempner. Does the atmosphere affect the spectral results? And I think you just alluded to that a bit.
Yeah, that's right. If you capture this like any object, especially we see the sun, the sky gets red, the sun gets red as it gets closer to the horizon. That extinction happens in spectroscopy too. So if alberio was just rising or just setting, this would have even more red here. And so the atmosphere does affect it. Not dramatically. It's not really a big hassle for most of what we do with the slitless spectra. But it's important to, if we're doing comparisons, have them in the same part of the sky, and in general be above, say, 40 degrees above the horizon, just to eliminate most of the reddening that occurs. That's a good and insightful question. And
not dealing with a plume of Saharan dust like we are here in the Southeast United States, right?
Oh yeah, there's that too. There's that too. It's,
yes.
Just a quick thing. The reason I've enjoyed doing spectroscopy is because your questions are good ones, but you can have great fun even discounting all of that, because all you're really looking for, and you can see it here in this slide, is that little dip right there,
right,
which if we spread this out, we'd see is right there. So go ahead. What else, Joe?
Perfect. Justin also asked, any spectral changes to quasar integrated over time, detectable and plotted data using the RSpec software?
Good question. I don't know. I meant to say before we started the Q&A that you'll stump me easily. I don't know the answer to that. But over time, there are things that you can, I hope I don't have anything revealing up here. I don't. I've got the Far Side. By the way, he's publishing you're a Far Side character or fan. But what I wanted to show you was on the RSpec site, under samples, are a lot of the samples I just showed you here. But what I wanted to show you, L-Y-R-E, L-Y-R-E, there it is. So here is our Lyra over 2 hours. I'm going to play a little video if I can find it. I'll click on the image. I guess I made it clear there. Watch this video over 2 hours done with a 4-inch refractor. Watch the change in the shape of that line. Not only do the hydrogen bomber features come into clear view here, but it gets much hotter right down here in the blue range. 2 hours. Now this animation wasn't done in my software, but you can capture this kind of data. That's pretty cool. I mean, I love this. What else?
Absolutely. Justin did also ask, what's the software language required to write this program? So more of the techie stuff with the software development.
Well, you can write it in anything. I don't, well, I'll tell you, I'm always a little embarrassed because it's not C# or C++. It's Delphi. And if you're not familiar with Delphi, that's because it's a little bit of a second-tier language, but it allowed me to port the software to the Mac in a week or two. We have a Mac version of the software for the classroom, for this thing, or for the little classroom gas tube spectrometer, but there isn't a Mac version for astronomy. I've not taken the time to do that. Sorry, Mac users, there aren't enough of you to make it worth my time.
We hear that often as Mac users. So.
But I'm thinking about it. I really am. In fact, for those of you who can see the postage stamp view of me, that whiteboard in the background is a list of the things I'd have to add to the Mac version. The problem is I can't erase that stuff because it's been up there for about 3 years, and it's just, it's permanent on that.
It's permanent now, right?
Exactly. What else? Oh, well, while you're looking for something, let me interrupt you. This was the other prop I wanted. It's so stupid, I'm embarrassed. But I was talking about averted vision. How's that for averted vision? You can't get better than that, can you? Both sides. So there you go.
Wonderful. Well, I'll go ahead and open up the microphone now to anybody who wants to ask any additional questions.
Great.
Yes, Tom, I have a question. You mentioned, I don't know how to pronounce it, Auguste Comte,
Yes.
who said we'll never know what stars are made out of.
Yes.
What kind of scientist was he?
He was a French philosopher. I don't know if they really had categories of scientists, because that was like in 1835. It's a good question. I don't know much more about him except that quote, which is used to ridicule French on some occasions. But Bill, I was planning to really give you a hard time because I heard that you got thick skin and that you deserve it both. But unfortunately, I didn't get there. But that's what they're saying behind your back before the meeting starts. Is it true?
You're going to have to ask them, I guess. Okay. Okay. Go ahead, bring it on. I can handle it. I'm from Chicago.
That's the attitude I like.
What other questions do we have?
I do have another question. You showed us a spectrum of a star superimposed over the spectrum from the moon. and there was a lot of hydrogen being shown on the moon. And I know there's been a lot of talk of that lately, but is that the hydrogen that that spectrum was showing?
No, it wasn't. That's a really good question. The first time I've asked it, or I've heard it. I don't know the answer. No, that's not hydrogen on the moon. I think that's probably the reflection of sunlight on the moon.
Okay.
Most of what, the moon is basically inert. In fact, even it's a good question because it brings up that issue of reflected light. So the sun has a lot of hydrogen on it, and so that was the absorption line from the sun, I'm pretty sure. But that spectrum I showed of Neptune, in order to really see those methane lines, what that guy did was he subtracted or divided out the spectrum of a sun-like star, so that the only light we were seeing was the light that was different than the sunlight that was hitting the planet, the contribution of the planet to the sun spectrum after it bounced off. But that's relatively easy to do too.
Okay, thank you.
Sure, thank you. Great question.
Bill Pellerin had asked, what kind of new science can be done with the AAVSO spectral data? So that was kind of getting to where I was going to, to a question I was going to ask myself.
Ask Stella and Arnie.
There you go.
I don't know. Because I'm not a photometrist, I haven't even been that familiar with the work they do, except that it's applauded in all areas of our field. I think the sense is that this data becomes archival data for people to go back and look at when they're interested in historical changes that have occurred. As I mentioned, the pro-am world is unfortunately not as developed in spectroscopy. There's an American astronomer in Italy named Steve Shore, who a few years ago solicited the help of some more advanced amateur spectroscopy participants. And he did the right thing, and that was he fed them every week. He would write a mini essay. And he'd say, now, the spectra you gave me this week, it was on a fast-changing star. It was on a BE star, which is a type B star that has an emission line. That's what the E stands for, because it's thought that it has a dust ring around it that varies in angle to us. But so he wrote these essays and he explained to them what they were seeing. So they got all excited. But there has not been as much of that kind of thing going on. And I know Arnie originally, and now Stella in charge of the AVSO, want to reach out to the scientific community and see more of that kind of thing going on. There is in Europe a BE star database that the French maintain that a variety of members and contributors to that database have been named on a variety of papers that have been published, including the one that I popped up on the screen for a moment from the AAS a few years ago. So there are opportunities, but it's important for me, because I actually sell something, not to overpromise that you'll be solicited and be getting emails from scientists every day asking you for new data. One of the things that can be done also, I believe, is, and I'm trying to think of the name of the guy, he went from a camera company, went up to SBIG for a while, and now he's on a sailboat. But he is a supernova hunter, and you'd know his name if I could remember it. But apparently there's a ton of supernovas out there that supernovae that are never identified as to their type. They're sort of a backlog. Well, the good news is that we've got the time to do it, and we can pick some of those off. And if they have that deep dip, we know that they're a type 1A, for example. The bad news is, and this is a question if it hasn't been asked, will be, and I'll provide it for you, and that is that, how deep can I go with a star analyzer? This is an important question, because normally when we're imaging normal stars without a grating, the star's photons, all of those photons that come through our telescope and through the atmosphere and hit our sensor are on a handful of pixels, right? Well, now take that same total number of photons and spread them out way across the sensor. Now they're spread out across hundreds of pixels. You lose about 5 or 6 magnitudes when you put a grating in the light path. So if you can normally image down to magnitude 15, you'll be able to capture stars down to, say, 10 or 9. There's tons of interesting stars to look at. You can stack these images. You can do darks. Eventually, though, if you go for a few years and that becomes something you want to do, you want to get to dimmer and dimmer objects, then you step up to a slit device, which can go much deeper for a variety of technical reasons. So what else?
Go ahead, and if you have a question, go ahead and unmute yourself and ask away.
Joe, I have a question.
Sure. Hey, Chris, how are you?
I'm great. Hey, really good talk, Tom. Appreciate it. I'm a real novice, so this is going to dial us back a long way.
Not a problem.
If I have a nebula that I'm trying to see,
Yeah.
and I understand the emission bands from that nebula, would that guide me to a filter that would help me see that nebula?
Yeah, it would. I mean, but there's people who know far more than what knuckle draggers like me might be able to discern from that. But you could confirm what other people say. Absolutely. If you have, a helium or hydrogen line, then you know that's where your data is. And so that's a great question. So you're no longer a novice. In fact, I have the luxury that I can say things like this. What's with the name novice? That name novice for this group is sort of not a popular name. You need to come up with a synonym for that that's better.
Enthusiasts, right? There we go.
Well, enthusiast sort of, I don't know. Anyway, that's my contribution.
But just to, again, just that would, I'm just trying to see a nebula.
Right.
I've got pretty basic goals.
Yes.
And I'm looking for some technique or piece of equipment that'll help me do it in and around my home. Now I've got a lot of light pollution, so that's probably part of my problem. But I just want to understand the concepts, and it sounds like I've got somewhat of a grasp on it.
Absolutely. It's an ingenious way of looking at it. And it's why newcomers often come up with ideas that people who are more familiar with the field don't, because not a lot of people have thought about doing it that way. I would say that the cost and the learning curve and not only learning about spectroscopy, but perfecting your imaging of dim objects is probably not the best way to spend your time right now. I talk to some people and ask them, what do I need to observe this object? And as you said, light pollution filters are very popular, and different type of nebulae require different types of filters, and that's something a lot of the members here in the club may be able to help you out with. But theoretically and practically, that is doable. It's a great question. You understand what it is that we see when we see an emission spectra. And for those of you who are wondering about that question, just very briefly here, I was going to show it, but instead I, for some reason, started Quicken on another screen, which isn't exactly what I wanted to share with the group. I can't bring it up. I was going to show the nebula image from my slideshow, but let's skip that for now. What else?
Again, if you have questions, go ahead and unmute yourself and ask away.
Good.
Tom, I apologize. I interrupted you.
No problem. I just wanted to show this slide. So what he was just asking, he said, when I try and image this object, let's pretend these aren't visible. I don't get it because it's too dim. Mm-hmm. But if I could just select and look at only the colors that were here, that were in it, I'd get brighter images. There'd be less noise from the street lights. And in this case, if you had a filter that just allowed ionized oxygen, then you wouldn't get any of the sky background that is causing this image to be dim. It's not a great explanation. It's the first time I've tried it. Anyway, what else? So Deborah, how'd I do? Come on.
Oh, great. Thank you so much, Tom. It was actually a topic. I was thinking of new topics as one that it wasn't on my radar. So I really appreciate your bringing it up. It was like the fairy godmother of topics came across just as I was planning the second half of the year.
Yeah.
So thank you so much.
My pleasure. I'm happy to meet you guys. And if there's anything I can ever do to help any of you, you know how to reach me. And carry on and have a great evening. I'm going to check out, and you all can hang out if you want.
Appreciate it, Tom. Thank you very much. Before you go, I was going to ask you, do you have anything coming up in Sky and Telescope we should keep an eye out for?
No, I don't. Okay. I'm actually working with a professor in Montreal who's going to describe some of his students doing spectroscopy as well as doing some photometry, and we're going to see if we can get that published. My goal is to popularize spectroscopy. I have a side benefit that I sell more product, but really the main thing is that amateurs like all of us here in this meeting, most mostly 5-10 years ago didn't know this kind of thing was possible.
Right.
And even today, many don't. So that's what we've got coming. Thanks for the question. And again, let me know if there's anything I can do to help.
Appreciate it. Thank you, Tom.
Sure. Bye.
Have a wonderful evening.
Yep, you too.
And for everybody else, remember our general meeting is tomorrow night. So please register for that when you get a chance. And we'll see you online tomorrow at 7. Thank you very much. Have a good night.
Thank you, Joe. Thank you, everyone. Nice
Bye-bye.
seeing
Good
everyone.
night.
Bye.
See you.
At all?